We have seen that Git is a persistent map, but you probably don't see it as a map. You see it as something more than that, something that tracks your files and your directories, a content tracker. Let's see what that means. We need an example project, so I built a very simple one, a cookbook. In the root of the project, there is a file named menu.txt. This is supposed to be a menu, a list of all the recipes in the cookbook. Right now it only contains a single recipe, apple pie. Then we have a recipes directory that contains a readme that tells you that you are supposed to add one separate file for each recipe here. And indeed, we have one file here with the recipe of the apple pie. This file is supposed to contain the entire recipe. For now, it's just a placeholder actually, and it contains the string apple pie. I'm using this string a lot here. I like apple pie. We'll fill in the real recipe later. So we have 3 files, one in the root and 2 in the recipes folder. It's a very simple project, but that's what we want for now. We want to understand how Git stores these files and folders, so it's better if we start simple. Let's make this a Git project with Git in it. There, now we have a .git directory here. And because it's a brand new project, the object database in the objects folder here is empty. Apart from the info and pack subdirectories, we can ignore those as usual. Now that we have a project, let's create our first commit for this project. Let's use the git status command to see the files and folders in the project root. You probably used the git status before. I configured my Git installation to use color, so we can see that both menu text and the recipes directory are red because they are untracked. That is, Git doesn't yet know what to do with them. You know that to commit a file, I have to put it in the so-called staging area first. It's like a launch pad. Whatever is in the staging area will get into the next commit. We can add these files to the staging area with the git add command. Let's add the menu text and then the recipes folder and all of its content. Now the files are green. It means that they have been staged. Let's commit them. I will use the -m argument to git commit so that I can give a commit message right here. There, now the staging area is clean. And we can use another popular command, git log, to look at the list of existing commits. There is only one, and its hash starts with these digits. Okay, good to know. So far, this was business as usual for any Git user. Now let's go deeper. Let's open the hood and look inside the Git object database. This is going to be short but intense, so hold on through. If you look in the .git directory under objects, you will see that we have a bunch of subdirectories in here now. One of these is named with the first 2 digits of the commit. And here are the remaining digits, so this file must be the commit. A commit is compressed, just like a blob. But by now we know how to pick inside compressed files, so we can use git-cat file for that. I will git-cat file the commits shown with -p so that it prints the content of the commit. And here it is. So what's a commit? It's a simple and very short piece of text, nothing else. It's truly as simple as this. Git generates this text and then it stores it pretty much the same way it stores a blob. It adds a small header to this text to say this is a commit, it generates its hash, it compresses the text, and it stores the result in a file in the object database. The commit text contains all the metadata about the commit, the name of the author, the committer, both are myself, the date of the commit, and the message. And then it contains something more, the hash of a tree. What's a tree? Well, just like a blob is the content of a file stored in Git, A tree is a directory stored in Git. The commit is pointing at the root directory of the project. That's what this tree is, the root of the project. If you look in the object database, you will see a directory named with the first two digits of the tree's hash. And inside it is the tree, a file named with the remaining digits of the hash, as usual. It's just like a commit. See, a piece of content that is generated by Git and then hashed and stored in the object database. So what's inside this tree? What does it look like? Let's catfile it. Just like a commit, a tree is a tiny piece of text. That's all it is. And it contains a list of the content of the directory, a list of hashes, actually. In this case, we have a blob and another tree with their names. The blob is the menu text file that's in the root. And the tree is the recipes directory that's also in the root. There is also some additional data for the files and directories access permissions, but otherwise that is it. That's all it takes for Git to store a directory. Now, if you have great memory for hexadecimal numbers, I don't really, then you might find the hash of this blob familiar. It's the same hash as the apple pie string that we've seen earlier. Let me prove it for you. I will use catfile -p as usual, pass it the hash of the blob, and there it is, the string apple pie. That's what's inside menu text. So to recap, the commit points to a tree, the root, and this tree points to a blob, menu text, and another tree, recipes. And the blob is just a piece of content, the string apple pie. Now let's finish the job. Let's look at this other tree and see what's in there. Let's use catfile again to peek inside the recipes tree. And there you are, two blobs. One of these blobs is the readme file. I will catfile it. Here, there it is, the content of the readme. The other blob, well, this one looks familiar even to me now, even if I can't remember numbers, because it's the same hash as the menu text blob. That's because these two files have exactly the same content, so Git will not create two separate objects for them. It will just reuse the existing object that is already in the database. So, to be picky, a blob is not really a file. A blob is the content of a file. The file name and the file permissions are not stored in the blob, they are stored in the tree that points to the blob. You will see in a few minutes why this is a good thing. For now, let's update our diagram of the object database. The recipes tree is pointing at the blob with the content of the readme file, and it's also pointing at the blob with the content of applepie.txt, which is the same content as the menu text file, so it's actually the same blob. And there you are, the whole object database, all of it. One small note about this: if you try building this exact same project and you use the exact same comments that I used here, then you will see that you get the same hashes for all the trees and all the blobs. However, the hash of the commit, that one will be different, because you have different data in your commit, a different author and a different commit date. The important thing to understand here is that there is no magic behind the shown hashes. If you have the same content I do, then you get the same hash. A commit is also just a piece of content, and your commit has different content than mine, so you get a different hash. It's as simple as that.